Good day to everyone. So today my lecture will be on sample preparation for gas chromatography. So class. In analytical chemistry, sample preparation refers to the way in which a sample is treated prior to its analysis. Frequently, the component of interest is present in levels too low for detection. Therefore, sample preparation can concentrate the component to adequate levels for the measurements. The presence of the interfering matrix elements can mask the analysis of the component of the interest. So basically the sample preparation can remove the excess contaminants to yield clean and informative chromatographs. For gas chromatography, sample preparation are needed due to the requirement that samples for GC be vaporized in the inlet. In most cases, the analytes must be distributed in an organic liquid or a vapor phase prior to the injection. Gas chromatography requires many specialized sample preparation techniques due to the requirement that the sample for GC be vaporized in the inlet. So the analyte must be distributed in an organic liquid or a vapor phase prior to the injection. The sample matrices and interference that may be present further will complicate the analysis. As a result, there are a tremendous variety of sample preparation technique available for gas chromatographers. In this lecture, a very basic overview of the principles, practice, and applications of the major sample preparation technique for gas chromatography will be provided. Okay, students, the type of the samples for gas chromatography. The samples that is injected into the gas chromatography following the sample preparation, either it can be in a liquid or gas. Okay, the analyte must be volatile enough under the condition of the inlet and the column to transverse the instruments, and ideally the matrix interference must also be volatile so as not to contaminate the instruments or column. The basic goal of the sample preparation is to ensure that these conditions are met, with additional goals that the preparation be reproducible to meet the quantitative analysis requirement and straightforward to perform. Other sample preparation objectives will be to pre-concentrate the sample and to interference the elements. Basically, class, when we do the sample preparation, okay, a proper or a suitable sample preparation technique, basically it will enrich the sample. Okay, in a way it will increase the sensitivity for the detection, and another, the main important thing is to eliminate the interference. Okay, so class, let's move on to the overview of sample preparation technique by sample type. For example, solid, dissolving followed by the liquid technique. Okay, there is some supercritical fluid extraction, headspace extraction, accelerated solvent extraction, pyrolysis, thermal desorption, and microwave assistant digestion, usually for metals. Okay, so the liquids and the gas. So here, class, you can refer what type of the sample preparation techniques, okay, we can use by according to the samples. So here, so students, as for the liquid samples, we can use macro liquid extraction, micro liquid phase micro extraction, solid phase extraction, and solid phase micro extraction. Okay, students, let's move on to the liquid extraction. Liquid extraction is the most classical way of the sample preparation techniques. In liquid extraction, dissolved components are transferred from one liquid phase to another. Most of cases, okay, in GC, this is performed to transfer the analyte from an aqueous phase to an organic phase that is more amenable to gas chromatography analysis. The main requirement is that two liquid phases be completely miscible. In most cases, this will involve the extraction of the analyte from a dilute aqueous phase into an organic phase. Often, for trace analysis, the analyte concentration The procedure also will introduce the concentration step to improve the sensitivity. So now let's move on to the macro scale liquid extraction. As for the macro scale liquid extraction, the main advantage for the of this extraction is the simplicity and potential for concentration of trace samples, and the disadvantage is actually difficult of automation, and large amount of high purity solvents will be consumed, and we have to find a way to dispose all that solvents, which is this way of the extraction technique is not a very environmental friendly techniques. So therefore this macro scale liquid extraction, basically it's not very encourageable, okay, at this point of time, due to the consumption of high amount of the solvents, okay. And basically this extraction will be carried out as shown in the figure here, okay, very classical way using the separating funnel techniques, okay. So students, let's move on to the micro scale liquid extraction. The main idea of the micro scale liquid extraction is to avoid the consumption of the organic solvent in the large amount. So for the liquid sample, we can use single drop micro extraction as shown in the figure here by using a micro syringe like aqueous, okay, into the aqueous sample with the help of the stirrer, okay. It's very simple technique. The main idea is actually we will use a single drop of organic solvent is suspended into the aqueous phase, and the system is agitated to drive the organic analytes into the drops. The organic drops can then be transferred to the GC for the analysis. And another technique, very famous technique, is dispersive liquid micro extraction. In this techniques class, dispersive liquid micro extraction is a miniaturized LLE using microliter volumes of extraction solvent, which is based on the equilibrium distribution process of the target analytes between the sample solution and the extraction solvent. So here class, the solvent will be dropped into the sample solution by using the syringe, okay. Then we can, the cloudy state will be formed as shown in the figure B, okay. The sample will be centrifuged for few minutes, then we can get two layer, okay. Then the down layer, which is the extracted layer, okay, will be withdrawn by using the syringe. Then we can inject into the GCMS or GCFID. But class, make sure, okay, when we do this technique, you have to be very careful, and you should not withdraw the aqueous solvent, which is the water. We cannot inject water into GC, as we know. So that's why you have to be very careful when you handle this. So you have to make sure you withdraw only the organic solvents, okay, so that we can inject that into the GC. Okay class, now as for the dispersive liquid micro extraction, which involve two types of organic solvent, which is extraction solvent and disperser. Extraction solvent can be acetonitrile, it can be any types of extraction solvent, and we must also use the disperser. Basically, it's a water soluble solvent such as methanol, acetone, or acetonitrile, okay. Of course, extraction solvent and disperser should be different. So first, the mixture of the extraction solvent and disperser will be injected into the water samples. Then the mixture of the sample and organic solvent are centrifuged, it will be centrifuged to separate the extraction solvent from the water samples. Then finally we will inject into the GC. So class, these are the example of the procedure, okay, as shown in the figure here. You may refer to these. So now class, there is another one method, which is by using the ionic liquids. So actually NTF2, lithium, C18 min, NTF2. So all these are different types of ionic liquids, okay. We can also use the ionic liquids to extract the analytes, okay, in this liquid phase micro extraction. So let's move on to the solid phase extraction class. Solid phase extraction basically it applies the principle of liquid chromatography to trap an analyte on a solid sorbent from a liquid matrix for concentration, cleanup, and phase exchange prior to the analysis. Basically, the analytes in the water are trapped on the solid sorbent under the condition of high capacity factor and then eluted with a small volume of strong solvent with a high capacity factor. So in solid phase extraction, the samples will undergo a few steps such as conditioning, sample addition, washing, and elution. So condition usually will follow the step use water followed by methanol and hexane. Sample addition usually non-polar, semi-polar, or polar. Uh, we have to follow the order of the, we have to check the nature of the sample, whether the sample is polar, semi-polar, or non-polar, so that we can use a suitable solvent for the elution. And we can also use washing. Usually washing will be done by using methanol. Then finally elution, in this case they are using hexane. Okay, so it's a non-polar solvent as for the elution process. So now class, these are the example of the SPE manifold. Okay, and these are the example, and the figure here it shows the SPE cartridge with the pumps and the SPE cartridge. Okay, consists of the C18 sorbents. Okay, and there is there is pump here, so basically we can control the pressure. Okay, so okay, student, let's move to the reverse phase. So the given example of the sorbent, SPE sorbent, all these are reverse phase. Okay, for example, LC18, the octa-decyl bonded, which is N-capped silica. So all these are silica-based packing. Okay, it's meant for the reverse phase, and some of the sorbents are suitable for certain types of analyte. Okay, so you can refer the given table here. So class, let's move on to this table. This table refers to the different types of material which is meant for the normal phase, and another one is for the as the ion exchange phase. So there are certain types of analyte, they prefer ion exchange, and some reverse phase and some normal phase. Here, for example, if you want to analyze the herbicides, pesticides, or alpha toxins, so you may consider LCCN, which is cyanopropyl bonded, okay, N-cap silica type of SPE cartridge, okay, for the extraction. And if we want to analyze the anions, organic acid, nucleic acids, nucleotides, or surfactants, so probably we need quaternary amine bonded silica with chlorine ion as the counter ion. Okay, so probably we can use this type of SPE cartridge. So when we want to choose the SPE cartridge, basically we have to choose whether it's a reverse phase, normal phase, or ion exchange. Is based on the property of the analyte, whether the property of the analyte is polar, non-polar, or neutral compound. Okay, so but most of the cases we will use the reverse phase if the under normal condition. Okay, but again it depends on the type of analyte that we are going to use. So this table here shows the another type of SPE sorbent as well. Okay, so alumina based packing, there is fluorosil based packing, graphites, resin based packing. So all these are suitable for certain types of analyte. Okay, all the description here is very detailed, so you may refer to this table, okay, later when you do your revision. So class, the retention process and the elution process that happens in the SPE, basically this is one of the example. So let's say retention, actually when the pH is less than 8 for this case, so the analyte has the permanent negative charge. As the elution, so that means class, the retention is due to the ionic interaction. So that means positive and negative charges, okay, it interacts together. Well, elution is actually the analyte will elute from that means it will wash out from the surface of the sorbent, okay, the SPE sorbent. So basically in this case the elution happens by the addition of the high ionic strand buffer. So basically when we add the high ionic strand buffer, the analyte will displace from the sorbent due to the competition with other anions. So the elution can also be accomplished by the application of the solvent of pH 12 or above, which neutralize the charge of the sorbent. So this is how it will happen, and it will become a neutral class. So neutralization of the charge, sorbent charge. So you may refer to this figure for further understanding. So class, basically SPE has replaced the LLE in many laboratories because in SPE we can reduce the large amount of solvent usage. Okay, and SPE also give the ability to carry out the extraction in the field, and we can avoid formation of emulsion as LLE. In SPE we can avoid that, especially when we are analyzing wastewater or biological sample. And the SPE cartridge also consider disposable, and actually we can reuse that or regenerate that as well. And the SPE cartridge is actually made from a medical grade polyethylene, so therefore the contamination that occurs from poorly cleaned glassware is very unlikely to happen. And solvent to be used in the SPE also, it's available easily. I mean, it's available in the market. Okay, and analytical chemists also can find the method of extraction in the application notes provided by the SPE vendors. So class, it's very easy. When you want to purchase the SPE cartridge, you can just ask your supplier to give the table. So what type of SPE cartridge is you can use for the type of the analyte that you want to analyze. Okay, so it's very easy and convenient way. And even class, you can find the manual or how to operate the SPE in the YouTube as well. Okay, there are so many videos in the YouTube. So class, now let's move on to the solid phase micro extraction. Actually class, nowadays, okay, people start to move to the another one technique, which is the solid phase micro extraction, which is in solid phase extraction we will use the solvent amount is in the large amount, while solid phase micro extraction is actually relatively a new sample extraction technique. Okay, and it will bring some unique capabilities to the chromatography analysis of the dilute solution in difficult matrices, for example in both liquid and gases. Okay, in SPME basically has two discrete steps. For example, solute absorption from the sample matrix into a thick layer of silicon or related absorptive material, and transfer of the analyte into the gas chromatography inlet. So now class, these are the example of the SPME extraction device. Okay, basically A is the fiber device with external soft coating, and B is the tube device with the soft coating inside that. Okay, the cross-sectional diagram of the SPE device shown here, and the SPME extraction from the sealed vial. Okay, shown in the diagram here. So basically the diagram here shows the sampling, the liquid sample, and the B is actually the headspace, okay, the gas phase. So this is how the example, the extraction is carried out class, okay, by using the SPME fibers. So now the SPME device with the microfiber, okay, in the middle item class, that is the microfiber. So how we are using the SPME fiber, so this is how we will use the SPME fiber. It's very fragile, and if you have to handle the fiber, because the fiber is actually very small, so we have to handle it carefully. Okay, so these are the example of the extraction class, how we will perform that extraction. Okay, so the best SPME fiber choice for the extracting analytes. So the given is actually the type of the analyte, and the first choice and second choice, third choice of this is the type of the SPME fiber that we can use for the analyte. Okay, so now class, let's move to the solid samples. As for the solid samples, we can extract the solid samples using the Saltpeter extraction, ultrasonication, accelerated solvent extraction, microwave assisted extraction, and supercritical fluid extraction. As for the sample preparation technique by sample type class, for example solid, we can dissolving followed by the liquid technique, which is for solid, and the supercritical fluid extraction, H-plate extraction, all these are for the solids. So now class, basically, a more advanced extraction technique is only required where the desired compound has the limited solubility in a solvent and the impurity is insoluble in that solvent. If the desired compound has a significant solubility in a solvent, then a simple filtration can be used to separate the compound from the insoluble substance. So class, let's move on to the Socklet extraction. So here, this is how the Socklet extraction will be performed. Okay, so the solid materials that containing some of the desired compound will be placed inside the thimble made from the thick filter paper, which is loaded into the main chamber of the Socklet extractor. So the solvent will be heated to reflux, then the solvent vapor travels up a distillation arm and floats into the chamber, and the condenser will ensure that any solvent vapor cools and drips back into the chamber housing the solid material. So the procedure is actually class, okay, we can perform this in the laboratory, under water bath condition. So the advantage of this extraction is the displacement of the transfer equilibrium by repeatedly bringing the fresh solvent into contact with the solid matrix. No filtration of the extract is required, but the disadvantage is agitation is not possible, and the possibilities of thermal decomposition of the target compounds cannot be ignored, as the extraction performed, okay, at the boiling point of the solvent for the long time, and the extraction time is quite longer, which is not very convenient class. So class, let's move on to the ASE method. So basically ASE method is a solid liquid extraction process performed at the elevated temperature, usually 50 and 200 degrees Celsius. So at the pressure between 10 and 15 millipascal. So the ASE is the form of pressurized liquid extraction. Okay, with the increase of temperature, it will accelerate the extraction kinetics and the elevated pressure, which keeps the solvent in the liquid state, thus achieving the safe and rapid extraction. It also high pressure will allows the extraction cell to be filled faster and helps to force the liquid into the solid matrix class. Okay, so the advantage of this method compared to the Saltpeter extraction, actually ASE can present a dramatic reduction in the amount of solvent, and extraction time can be done in minute. The disadvantage is the particular attention should be paid to the ASE performed at high temperature, which may lead to the degradations of the compound. So these are the disadvantage of this method. So class, let's move on to the supercritical fluid extraction. Supercritical fluids are dense gases above their critical temperature and pressure, possessing the gas-like viscosities and diffusities, and having the densities and solvating properties that approach those of a liquid. The properties of supercritical fluids make them ideal for extract the analyte from solid matrices such as soil, agriculture product, foods, and solid sorbents. Two factors that play a role in the extracting the analyte from a solid matrix by supercritical fluid extraction. Basically, the analyte must be soluble in the supercritical fluids, and the analyte solvent interaction must be energetically favorable than those of the analyte matrix. So here class, Given is the example of the phase diagram for carbon dioxide. So take note of the y-axis will be the pressure, x-axis will be the temperature. So the PC will be the critical pressure, okay, and the TC will be the critical temperature, and CP will be the critical point. So class, and the phase diagram is actually divided into solid, liquid and gas, and the TC value, which is the critical temperature value, will be 31.1 degrees Celsius, and PC will be critical pressure value will be 72.8 atmosphere. Okay, the pressure will be 72.8 atm, and in the diagram also, you can also uh, observe the critical fluid region. Okay, it's above the liquid region. So class, the given table shows the physical properties of a compound, okay, commonly used as a supercritical fluids. For example, the fluids that commonly used will be the carbon dioxide, okay, nitrous oxide, ammonia and so on. The critical temperature, critical pressure and the dipole moments, okay, are given here. Okay, so these fluids are the common fluids used in the supercritical fluid extraction. So class, these are the example of the instrumentation for the supercritical fluid extraction. So basically, carbon dioxide, okay, will be used as the supercritical fluid. So what is happening here is basically the solvent trapping in SFC, okay, will be done, followed by the trapping on the solid sorbent. So this is how the extraction process will occur in SFC. Okay, you may refer to the YouTube for the further information, class. So now, SFC has two modes of extraction, which is dynamic and static. In the dynamic mode, the sample matrix will be continuously flushed with the fresh supercritical fluids, which pass through the sample matrix, solvate the analytes and carry them to a trap where the analytes are collected. While in the static mode, the sample is placed into an extraction vessels filled with supercritical fluid at the appropriate temperature and pressure, and allow them to stand for a period. When the extraction is completed, the supercritical fluid will be released through a trap to collect the analytes. While static extraction also allows the analytes with slow mass transfer time to be solvated by supercritical fluids. So the advantage of this extraction compared to the liquid extraction will be basically it's relatively rapid because of the low viscosity and high diffusities, okay, associated with the supercritical fluids, and also no organic solvents are involved in this extraction mode. So the disadvantage of this mode is expensive instrument. So that's why most of the place, very difficult to get this kind of extraction. Basically, engineering department will use supercritical fluid extraction for their application. So okay class, let's move on to the ultrasonication method. So in this method, basically sonication will be used, okay, in order to extract the samples, okay, the solid samples, and the samples will undergo the filtration process for the removal of unwanted solid samples, and this procedure is quite simple, okay, and it's available in our lab. Okay, so now let's move on to the gas samples. As for the analysis of volatile organic compounds in the air, so many substances that harmful to human health are detected in the atmospheric air. So even substances that are not at a concentration level that has a direct effect on human health may also concern of carcinogenicity after a long-term exposure. So in general sense, VOCs in air are sampled and measured by three mechanisms, which is tubes, Tetler bags and canisters. So In order to extract the gas samples, so the first method is the tube methods, which is cartridge or is just a traps. Okay, the tubes is also refers to the cartridges or the traps, which are filled with the adsorbent material such as the charcoal or carbon molecular sieve. So the samples is drawn through a tube by a gas sampling pump, and the VOCs are adsorbed by the adsorbent materials. Concentration and sampling occurs when the sample is drawn through the tube. So this is how the VOCs will be trapped, okay, by using the tubes. Okay, class. So in order to extract the gas samples from the environment, another way apart from the cartridge, we can also use Tedlar bag and the canisters. So canisters is actually a stainless steel containers. Okay, with the canister sampling, a valve will be open and the air samples is either pumped or drawn into the cylinder. So the samples is shipped to the lab for concentration and the analysis process. Sampling of the Tedlar bags is achieved by pumping the air sample into the polymeric bag. Okay, and then the Tedlar bags are basically an inert material and have been designed not to absorb the VOCs. So by using the Tedlar bag and canisters and the cartridge, so basically we can analyze the gases from the environment. So class, now let's move on to the comparison of the sampling techniques. So canister sampling and the analysis offers a complete range of the analysis. One can analyze low and high level of samples of polar and non-polar compounds in the canister system. So duplicate samples can also be taken from the canisters, and canisters can be diluted as well. Just that class, canisters are very expensive and the associated analytical equipment is more expensive. In the daily practice, environmental chemists usually they use the tubes because tubes are the cheapest route for the analysis for the analyzing the air samples, but just that the samples cannot be diluted or reanalyzed, and the analysis by using the Tedlar bags fits someplace between the tubes and canisters, but Tedlar bags also do not require as much as space as the canisters, but some VOCs in the bag may only be stable for a short period of time. So that's why to be in a safe side, and the best sampling method is actually the canister sampling, okay, by using the canisters. So with that class, thank you so much for your attention.